So I could use two variables and define a subproblem. Then these variables can be changed to different values, and the problem would like in the definition you will be using these parameters, and the definition will keep changing according to that. So here the definition is shortest path from u to v. Let me define it, p of u comma v. Okay, then p of 1 comma 2 would mean the shortest path from node 1 number 1 to node number 2. P of some 5 comma 8 would mean the shortest path from node 5 to 8, and something like that. Okay, so these two parameters uniquely define a sub problem, and my original problem is p of u comma v. That is what I want to find out. Now I will break down this problem into a relation. Okay, so first of all I'm going to divide and conquer this problem. I know that finding the shortest path from u to v is hard for me. So what I'll do is I will see what are the options from node u that I have. So from node u, I could go to any of the neighbors of u, right? From u, I could go to any neighbor. So if this is a neighbor, I could go here. If this is a neighbor, I could go here, and something like that. So if there is a node from u, like if there is an outward edge from u to some node, I could go from u to that particular node. And once I go from node u to some node x that is a neighbor of u, that means x can go to u, from u you can go to x. Sorry. Then from x you would like to find out the shortest path to v. Let's say this was node x. You will go from u to x, and that would be 1 added to your total path. From x you would like to take the shortest path and go to v. And what is that? By definition, it is another DP state with parameters t of x comma v. And this is a DP state. Similarly, if I go to some other node, let's say this is node y, then I would like to take the shortest path from node y to v, and that is nothing but p of y comma v, the shortest path from y to v. And you can clearly see that these two integers are totally capable of defining any subproblem. So and these parameters together will define a unique DP state. That's it. This is the idea, and the relation among these different DP states is known as the recurrence. So for Fibonacci numbers, the recurrence is f of n. That means the nth DP state depends upon the n-1th DP state and the n-2th DP state, and this is the relation between the nth, n-1th and the n-2th DP states. This is known as a recurrence. In the case of shortest path, you don't need to follow it. Like I'm just giving you the relation. If you don't even follow, it's okay, because this is a DP problem on its own. So if you're a beginner, it's okay even if you don't understand this, but I'm just giving you an example of a recurrence. So for the shortest path, 1 plus minimum, from u you will go to some child of u, and from that child c you would like to take the shortest path from c to v among all the child of c, among all the child nodes c of u. That means there is an edge from u to c. So among all these nodes that you can go visit from u, from that node child c you would like to take the shortest path from c to v, and that will be a recurrence for the shortest paths. So guys, that's the idea for DP state and recurrence. A DP state is a collection of parameters that uniquely can uniquely define a subproblem is known as DP state. A relation between different DP states is known as a recurrence. That's the short definition. Finally, top down and bottom up. So top down. So the top down codes are quite nice. In top down code, you will simply say, okay, I want to solve the big problem, and you will break it down into smaller subproblems, and you will go from the top, the main problem that you wanted to solve. You will keep going down till you reach a problem that is so easy to solve that you can solve it directly. In bottom up, the idea is that first you are going to solve the easier problems and then use their solutions to go upwards. So you first of all solve the easiest problems of all, use their results to solve a little bit harder problem, then use their results to solve even harder problems till you solve the hardest problem that was your initial problem, and you go from down till up. Okay, so top downs, usually beginners will find top down to be more intuitive, whereas bottom up requires a little bit practice. However, bottom up codes execute a little bit faster, even though both of them are asymptotically both of them will have the same time complexities. Implementing top-down codes is very easy. You will simply call a recursive function solve with all the parameters defining the original problem. Then that will break from there we are going to use the recurrence and keep calling the recursive function with by using different parameters for defining subproblems using a recurrence till we reach some base case. That means till we reach a problem that can be directly solved. So top down, simply write a recursive code that takes in all the parameters defining a subproblem, and also keep memoizing the results that you get. Okay, so you keep storing the results in an array so that you never solve a subproblem again. A subproblem will be defined by the parameters, so you could have a dp table for that is of the dimensions of the number of parameters required to store, like required to describe your subproblem. And that is the idea for top down. For bottom up, I'm going to discuss a more interesting approach in the next video. So guys, if you liked the video, make sure that you like, share and subscribe. Thank you for watching. Hi guys, this is Karthik. Welcome to the third part of the series on elements of dynamic programming. And first of all, thank you Jashan for suggesting me to have the Sublime in full screen. This really looks better. And now for this video, I'll be discussing three things. One is going to be the DAG representation of a DP solution. This is really important, okay? Something that will really help you. Second, we'll discuss how we can visualize top down and bottom up based upon DAG representation of a DP. Thirdly, we will discuss how to analyze space and time complexities of our DP solution. And this will also depend upon the DAG representation. And not 3 but 4, I will also discuss the evaluation order for bottom up. Okay, for top down it's easy, but in bottom up we have to think what needs to be evaluated first. I said that you should solve the easiest sub problems first, but how do we decide which one is the easiest or which one should be solved first? So let's start with the DAG representation. So the idea in the DAG representation is that in the previous video I told you that there are DP states. Each and every sub problem is basically a DP state with some parameters. So the idea is that we will make a graph out of the states. We're going to construct a graph, and in this particular graph our nodes are going to be the DP states, and the edges in the graph are going to be the dependencies among these states. Okay, so let's say that there is a state u, some DP of u. So there is a DP state u represented by the parameter u, and there is another DP state v. So let's say that DP of u equal to something something something, and it depends upon DP of v. Okay, it directly depends upon the result of DP of v somehow. It could be a max function among a lot of other DP states, or summation function or something. So DP of u depends directly upon the answer for DP of v. Okay, to evaluate u, you have to know the result for v before you evaluate u. Then there will be an edge from u to v in that particular case. Okay, if the recurrence for state u involves the state v in any form, then there is going to be a directed edge from node u to node v. So the idea is that the edges are going to represent the dependencies among the states, and there's going to be an edge from any DP state or any node u that represents a DP state u to any other node v in the graph. If DP of u, the result for u directly depends upon the evaluation of result of v, then there will be an edge, directed edge from u to v. And this is the idea. This particular graph will turn out to be a directed acyclic graph. And why is that so? Because there are going to be directed edges from like to represent these dependencies, and there can never be a cycle. Because if there is a cycle in this particular graph that represents your DP approach or solution, then this would mean that to evaluate the answer for you, you need to solve V. But if there is a cycle this would mean that to evaluate answer for u, you need to know v, but to evaluate answer for v, you need to know the answer for u. And this is something known as a deadlock. This cannot happen, right? So you have to solve one of them first, and therefore if there is a cycle in this particular graph, then you cannot actually evaluate your answers. It has to be a directed acyclic graph. Only then can you evaluate the answers for every node. So let's try out the Fibonacci and make a maybe DP state graph of a DAG graph out of it. Then I know that node 7 value and so node 1 does not depend upon anyone else. C is a directed acyclic graph. This actually evaluate 6 and 5 first. Then you will think about 6. This means that to evaluate 6 you need to evaluate 5 first and 4 first, and you will be able to evaluate these answers only once you will, let's say for node number 7, to evaluate okay it has a cyclic graph only. Now how does the bottom up work? Bottom up works in this way. It will evaluate 1 first, okay, because 1 is independent of any other node. Now it will try to evaluate any other node that can be evaluated only using the information of this node, and that is node number 2, because node number 2 depends only on the answer for node number 1. So bottom up will evaluate this guy. Then it will find another guy that can be evaluated using these informations. It will say okay 3, because 3 only needs 1 and 2, and therefore 3 can be calculated. Again, next it can evaluate 4 because all the people on which 4 depends are already evaluated. So 3 and 2 are done. So bottom up says okay, now I can go for 4. Next bottom up code will go for 5, because that is the next node it can evaluate, since both the nodes that 5 depends upon have been evaluated already. So it will go for 5, then 6, and then finally 7. This is how bottom up is going to work. Now let's try to evaluate the time and space complexities for a DP solution. Okay, so first of all, the time needed to evaluate a state which does not depend upon any other state, let's just assume it to be big O of 1. Okay, that's going to be constant time because a state does not depend upon any other state. Now think about some state node number u. U depends upon some k1 number, let me call this state number s1, and I'm saying that s1 depends upon some v1 other nodes, okay, some v1 other states. So this could be some states c1, c2 and cv. So I assume that to evaluate the answer for dp of s1, I need to know c1, c2, so until cv1. Okay, now let's see that what is the time that will be needed to evaluate dp of s1 if I knew these by beforehand. Also here I assume that the merge step is going to be big O of 1. I'm going to assume that it's a constant function that needs to be evaluated upon all these values. It's f of c1, c2, so until ck, and evaluating f is constant time operation. Okay, so in that particular case, since there are v1 values on which state s1 depends upon, my time is going to be proportional to big O of v1. Okay, so I'll just write v1 for now. Let's say I'm going to do v1 operations to evaluate answer for state number 1. Similarly, state 2 depends upon some other states, and I'll say that state s2 depends upon v2 states. So for state s2, I'll say number 1 proportional to big O of v1. Okay, so I'll just write v1 for now. Let's say I'm going to do v1 operations to evaluate answer for state number 1. Similarly, state 2 depends upon some other states, and I'll say that state s2 depends upon v2 states. So for state s2, I'm going to do another v2 operations, and till now in all I have performed v1 plus v2 operations till now. Similarly, I'll assume that v3 needs to know the value of v3 other people, s3 needs to know the value of v3 other people, so that will be v3 for that, and so on till the nth node. the nth DP state, assuming that there are a total of n nodes in my DP graph, then I will say that the nth node in my SN, the nth state of my DP graph requires to know Vn other values. It requires to know Vn other values. So I will have to look at all these values 1, 1, 1, and I can look at those values in big O of 1. That's my assumption. So looking at Vn such values is going to be big O of 1 into Vn. So I'm saying, okay, Vn operations will be needed to evaluate DP of Sm. So since I'm going to evaluate DP of S1, DP of S2, so until DP of Sn, I'm going to evaluate all of these. My overall time complexity for the algorithm is going to be nearly proportional to V1 plus V2 plus V3 plus so on till Vn, which is actually the number of edges in the DAG. Now I need to find out this particular sum. So it would be good if I could, if not in the exact sum, I could come up with an approximate sum. Okay, I would like to approximate this value. So let's just say that the average of V1, V2, V3, so on till Vn, let's just take that. So EV, expected value of the number of nodes. Let's just say that the expected edges coming out of a node EV equals to summation Vi upon total number of nodes. Okay. Instead, let me just say X, and X is the average amount of operations you need to do before you evaluate a particular state. Okay. This is the average amount of operations you need to do to evaluate a particular DP state. The number of edges coming out from a state, and X is the number of operations you will do before you are able to evaluate a particular DP state, DP of S. So on average per state you will be doing X operations. So what is going to be your overall operations that you perform? It's going to be N into X, and X equals to summation Vi by N, and Nx is going to be your overall time complexity. Your space complexity is obviously going to be big O of N, the number of states in the DP graph. Of course it can be optimized since not at all times all the nodes will be required. So depending upon the problem statement, this thing might be optimizable. But if you're evaluating each and every state of the graph, and per state on average you need to perform X operations, your time complexity is going to be big O of N, and your space complexity is going to be big O of N. Okay, so time is going to be big O of N into X. X is the average number of operations you perform before evaluating a particular state. But how does this particular time help us? So knowing the number of states in the graph is pretty easy. It can be evaluated from the parameters that describe a subproblem. Just just find out the total number of states in the graph that are going to be in the graph. Then time will be evaluated as big O of number of states into X. How do I estimate X? So instead of finding a tight upper bound, I will find a loose upper bound. Okay. And I will think about that one node which will be the most costly for me to evaluate. Okay. So let's say that I know that the node that is the most costly to evaluate will take me n time to evaluate. Let's say for example, the most costly node to evaluate in the graph is some node S1 and it takes me n time to evaluate. So to find out the loose upper bound, I will say that the average time is equal to the worst time. Okay, I will assume x to be the worst time, and then I will get a loose upper bound of big O of n into x. Finding x will be pretty easy for most of the problems. Let's take an example. In Fibonacci, there are going to be n number of nodes, so your space complexity is simply big O of n. Of course, you can optimize it, but let's just be naive at the moment. What about the time complexity? We discussed as n into 2, not n into 2, it's n into x, but here x equals to 2, and the maximum time taken to evaluate any node is going to be at most 2 operations, so it becomes n into 2, and therefore Fibonacci is big O of n. Okay, let me discuss one more. Think about the following recurrence: dp of I equal to 1 plus maximum over dp of j. So for all valid j less than I, and j can be anywhere from 1 to I, and we want to evaluate dp of n. Then there are a total of n states. Okay, since we want to evaluate dp of n, so there are n states. So space complexity is alright, it's big O of n. What about the time complexity? We will think about the hardest state to calculate. The hardest state to calculate is in fact the nth state, because for that I will need to know n minus 1 other values, right? dp of 1, dp of 2, dp of 3, so until dp of n minus 1. Also guys, don't try to optimize this thing, because I know this can be easily optimized, but refrain from doing that. This is to understand the time complexity and space complexity thing. So yeah, the nth state depends upon the first n minus 1 states. So I can say that the time needed to evaluate the worst state here is n minus 1, and I can take that, I can assume that the average time to evaluate any state is n minus 1. Okay, so I'm basically calculating a loose upper bound on the time complexity. So for every state I need n minus 1 time, so x becomes equal to n minus 1, and my time complexity, as we said, is big O of n into x, so it becomes big O of n into n minus 1, which is n squared. So this particular solution will run in n squared time. Now one last theory. This particular x, the time needed to evaluate the hardest state, or the state that depends upon most number of states, basically is known as the transition time. And your space complexity is equals to the number of states, whereas the time complexity equals to the number of states into the transition time. So guys, that's it. Also, one last thing, be sure to like, share and subscribe. Kidding. One more thing, the evaluation order, to find the bottom up, to write a bottom up code, you need to have an evaluation order of these states. And the evaluation order, as we saw, you first evaluate the state that depends upon no other state, then you evaluate those states that can be evaluated with the knowledge we have, and so on till the top. This particular order of evaluation is known as the topological sort of a graph, topological sort of a DAG. And you can read more about it if you'd like. I can make a video on this also, but the bottom up solution works in the topological sort ordering. Okay, and guys, that's it. Hopefully this was helpful. Thanks for watching. Hi guys, this This is Karthik Arora. This will be the first problem for the series on dynamic programming, and I hope this series really helps you to understand the various kinds of DP problems. Okay, so let's get started. So in this problem we are given with a number n and we are given with a dice. We would like to throw the dice again and again till the numbers that appear on the dice sum up to n. So let's say that n equals to 3 and you're given with a dice. The dice has 6 faces and each face has a number 1, 2 and so on till n is 6, right? So you can throw the dice again and again and you would like to find the various number of ways in which you could throw the dice to such that the sum totals up to n. So for example, if you had 3, I'll show you the different kind of possibilities. Yeah. So you want a total sum of 3. You can roll the dice and get a 1, right? Or you could roll a dice and get a 2. Or you could roll a dice and get a 3. I will not consider the possibilities of getting 4 and 5 and 6 because anyway those are not the ones I want to count, because then my sum, I've already exceeded my sum, right? So if I got a 1 on my first throw, I would like to get a sum equal to 2 now, right? By throwing dice again and again. So I would also like to find the number of ways in which I could make a 2. So here, to achieve a 2, I will roll a dice 1. Either I get a 1 or I get a 2. In the possibilities that you get a larger number, those possibilities you don't really care about because you exceed the required value. If you throw the dice and get a 1, then you would like to make a total of 1 now again. If you get a 2, you are done and you have made the sum equal to 3, and this is one valid way, this particular way. Okay, so you can throw a 1 and then you can throw a 2. So in 2 throws you will make the sum 3, and this is one valid way of throwing the dice. So you should count this in your answer. Yeah, so here you can again throw the dice and get a 1, and this is another valid way, right? Because now you have made the sum and the required sum now is 0, the one you want to make. So this is another valid way. You can throw the dice thrice and get 3 ones. If you had gotten a 2 on the first throw, then you would be left with making a 1 here, right? Because you have already got a 2 here. So now this required sum is 3 minus 2 equal to 1. You can throw the dice again and get a 1 and you are done. So this is another way. You can throw a 2 and then you can throw a 1. If you throw the dice and you get a 3, then you are already done. So 1 way, 2 way, 3 ways and 4 way. So there are a total of 4 ways to throw the dice and get a sum equal to 3, and that is the output here. So with this much intuition, let's move to the solution now. Yeah. So we can throw the dice any number of times, and we would like to evaluate the number of valid ways of throwing the dice, right? So I'm going to define dp of I as the number of valid ways to throw the dice, number of valid ways in which you can throw the dice such that the throws, the number you get in each of the throws sum up to I. So number of valid ways of throwing the dice. So that sum equals to I, right? Now with this thing having in place, dp of I is defined. So if I ask you what is the final answer, the problem asks us to find what are the number of ways of throwing the dice so that the sum equals to n, right? That is what the problem is asking us. So obviously if we follow this particular definition, my answer is going to be nothing but dp of n. Now all we are left to do is build up a recurrence for dp of I, and if we are able to evaluate dp of I efficiently, we will be able to evaluate dp of n. So let's see what dp of I will be. So I want to make a sum equal to I. I can either throw a dice and get a 1, a 2, a 3 and so on till 6. I'm going to get some number when I throw the dice. So if I throw a 1, this is one of the possibilities. I would like to find what is the number of ways in which I can make the sum I minus 1. Here I would like to find the number of ways in which I could make the sum I minus 2. Here I would like to find the number of ways in which I can make I minus 3 and so on till I minus 6. So what are the number of ways in which I can throw the dice so that my sum equals to I minus 1? By definition again, it is nothing but dp of I minus 1. So dp of I is going to be dp of I minus 1. If I throw a 1 on my throw, right, if I throw the dice and get a 1, plus dp of I minus 2 if I throw the dice and get a 2, plus dp of I minus 3 if I throw the dice and get a 3, and so on till dp of I minus 6. I could write this in a more succinct form also. Is going to be summation dp of I minus x. X is the number you got after throwing your dice, so x can be 1 and so on up to 6, and this will be your dp of I. This is a recurrence. I will discuss a few base cases and then I will quickly write a code for this thing. So first thing will be that dp of 0 will be defined as 1. The number of ways of throwing a dice to get a total sum of 0. The way is that you don't do anything, and therefore there is just one way, and that one way is doing nothing. dp of 0 is defined. How about dp of some negative number, right? Let's say if I had a die number 3, I throw some 4, right? So this is larger than 3, so this would be an invalid way, right? So either I can define what will be the dp of some negative number, or I can avoid doing something like this. And I will choose to avoid doing something like this in which I throw a larger number, right? Because anyway then my way is not going to be valid, so why should I think about it? So this is all. This is the base case and the recurrence. Let me just code this up and I will discuss the time complexity also. So let me have this integer dp array, and since n was up to 10 to the power 6, I'll keep this array as large as 10 to the power 6 only. So there are no t number of test cases. What I can do is I could say cnn, and then I can make a vector to store the intermediate values. Then for all the values from 1 till n, so I have defined this fr here. You can look this up. This actually helps in competitive programming. It adds a bit of seconds to, like, a little bit edge over the opponents, right? You get a better rank using such things. It adds a bit. So I have defined this fr here. You can look this up. This actually helps in competitive programming. It adds a bit of seconds to, like, a little bit edge over the opponents, right? You get a better rank using such things. So let me just define my base case. dp of 0 will be simply 1. Now dp of I is going to be if I throw x on my dice, right? If I throw the dice and I get an x, x can be either 1 or it can be up to 6. And my dp of I will be, yeah. So as we saw that dp of I was equal to the summation, right? So summation can be written using this for loop. dp of I plus equals to dp of I minus x. And what if x is greater than I? If x is greater than I will simply ignore this thing. So that's it. Once you're out of these loops, your answer will be stored at dp of n. So we're getting the correct answer. I'll just submit on CSES. Okay, one thing I forgot is that the number of ways will be very large, so I should print it modulo 10 to the power 9 plus 7. Let me just make this LL, no risk and no risk. Yeah, so it got accepted, guys. Hopefully this was helpful to you. I'll see you in the next video. If you liked it, do like, share and subscribe. Hi guys.